All right, gang. Math 6610. At this point, I think it's going to be advantageous for us to step back and take a look at the way the calculations are made for the sum of squares, different components of the sum of squares, and how we partition out the variance of each of these components. Now, I tell you what. Let's do this. All right, gang, Math 6610. At this point, I think it's good for us to pump the brakes a little bit and dive in a little bit on how we make these calculations. And these calculations being, could I be any more vague? These calculations being how we partition out the variances and how we calculate the sum of squares. Now, if you remember, the sum of squares calculation for repeated measures is we still have the total sum of squares partitioned out for the sum of squares between plus the sum of squares, easy for you to say, right, within. But in the within component, as we saw in the previous video, we can break this out into another component of sum of squares that are explained versus the error. Now, typically, your sum of squares within is your error, so what we do is we essentially just reduce this. And again, we saw that how that plays out in the previous video. And then the degrees of freedom for the model are just k minus 1, where k is the number of measurements. And degrees of freedom for the error, this component right there, is the degrees of freedom minus the degrees of freedom for within, minus the degrees of freedom for the model. And the easiest way to do that is just take n minus 1 times k minus 1. Now, n minus 1 is the number of measures, or actually the number of subjects, and k minus 1 is the number of measurements. All right, now again, we can do these calculations in R, but I really think in terms of teaching, I've done it both ways. And I think in terms of teaching this, I think it comes across better just using Excel. I'm not a big Excel fan, I'm not going to lie. But I think this is one place where making these calculations in Excel is to our advantage. So the very first thing we would want to do is calculate the sum of squares total. And to do that, we're just going to take the variance of all of the numbers times the total sample size minus 1. Well, we have 4 measurements over 8 people, so 32 minus 1 gives us 31. So the sum of squares for the total is going to be, let's just call it 253.9. Now, the next thing I would recommend calculating is the sum of squares within, because that seems to be the leg that has the most going on. So, and obviously if we can get the sum of squares within, getting the sum of squares between would be easy. Just take the sum of squares total minus the sum of squares within. So let's just come into the most complicated leg and see how those calculations are made. Now the sum of squares within, typically this measurement, this variation, and when I say typically, a traditional ANOVA really looks at the variation within the groups, right? It doesn't do that here. It looks at the variation within the person, within the subject. So we're looking at subject variation instead of group variation as we would do traditionally. Now, so what we do, as I say here, or as I should demonstrate here, we take the variance of person 1 times n minus 1. Again, n would be the number of measurements taken on that person, and just sum that up across all the people. Well, it makes it really easy because what we can do here is we can just go equal the variance of these measurements for person number 1. And we can just fill down and find all the measurements, in this case, which would be the variance. I'm going to clean that up just a little bit, or maybe I won't. Yeah, but I have to, whatever. I'm just being picky. So to calculate the sum of squares within, I would take the sum of these numbers, right? Times, having a hard time seeing here, the number of samples taken. So there would be, on each subject, there were 4 taken, so times 3, 4 minus 1. So there I get 236. 0.5. Sorry, and we've got our cleaning lady is coming at, well, she's supposed to be in here about 15 minutes ago, and I thought I heard her. So the sum of squares within would be 236.50. Now the next thing we need to do is we need to see how this 236.5 breaks down. So the sum of squares for the model switches focus on the measurements across, well, the different measurements. So now what I want to do, and let me come in and give me a little bit of space here. What I want to do now is I want to calculate the means for each of these measurements, and then subtract from the grand mean, and then multiply by the number of samples taken, which would be 8. So again, with Excel, this is very, very, very easy to do. Much easier to do than in R. So those are the means across each measurement. Now we need to come in and find a grand mean, so I'm going to just do this here. So the grand mean is 5.56, so I need to take that value, well, so I need to take 8 times that value minus 5.5625 and square that, right? Run it across. Now let's go in and just make sure that everything stayed the same. So we have 8, 5.6, because sometimes you get a autofill, which can be very, 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 well, can make bad calculations, right? So we need the sum of squares for the model. So that's just going to be equal to the sum of these values. and I get 83.125. Now, we can easily find the sum of squares for the error. That's just going to be found by taking the sum of squares within minus the sum of squares for the model. So we'll get 153.375. The only other variance or sum of squares that we need to take a look at would be the sum of squares between. Well, that's going to be very easy. So it's just going to be the sum of squares total minus the sum of squares within. Now, the next thing we would want to do is we'd want to calculate the degrees of freedom, and I'm just going to call it the degrees of freedom for the denominator. I'm sorry, for the numerator. Let's do it first. So that's just going to be the number of groups, which in this case is 4, minus 1. So the degrees of freedom there will be 3. And the degrees of freedom for the denominator, as we see over here, are the number of groups in each measure. So in this case, it would be 8 minus 1, which is 7, times the number of measurements is 4, minus 1 is 3. 7 times 3 would be equal to 21. Now, you should be able to see here that we can calculate this F statistic very easily by doing what? By taking the, well, I'll tell you what. Let's save that one until we get over into R. All right, because we're going to need the PF. Now, so what I want to do next is I just want to show you. So I need to really get rid of all this stuff. And I probably have impressed upon you by now that cleansing the data, setting it up correctly as we need in Excel, and then moving it into R is probably the best way. So I'm just going to create a subject variable. So at least I find it, and I consider myself to be decent at R. I can't. Okay, so we need M1, M2, M3, and M4, right? No, these should all be measure ones. That's fun. And these should all be measure twos. What am I doing here? Okay. Oh wow, I'm losing my mind. So these should be measure ones. Goodness. I don't lie, I'm distracted because something's going on outside, and I probably should end this video, but I want you to appreciate that what happens when you get distracted. All right, this may be one of the clumsiest videos I've ever created. You may argue against that. All right, so measure ones, let's just copy and paste those. Copy and paste those. I may have been able to actually do this quicker in R. I don't know. Be a heck of a lot cooler. All right, finally, let's get rid of all the garbage here. And let's save as, let's just call it demo. All right, that was easy. Okay. So let's grab our data. Attach it. And let's take a look at it. All right, so we are ready to run the repeated measures design. Now again, we can do this one of two ways. We can, the ANOVA feature, the AOV command. So let's just run it that way because I'm really not interested in sphericity just yet. I'm just wanting to focus this, have this video the focus of calculating the different sum of squares. So we have AOV, and we want our scores as predicted by our measure, plus the error component. We need a factor of subject over measure. So summary model. And you're going to see some values that have popped up over here. Over here being what you can't see. Now, so the 153. Okay, the sum of squares for the model, the 83.125, is the value you'll see right here. The 153 is the sum of squares for the error. That's exactly where you would expect it to be. The difference that we calculated for the factor subject, that's the difference in the 253 and the 236.5. So that would be the 17.38. Now this F value is just as you would expect. Take the sum of squares, which is again the 83. Again, the F statistic is calculated on these values. So it'll take the sum of squares for the model divided by its degrees of freedom, in this case to get 27.71. And the sum of squares for the error, which is the 153, divided by its degrees of freedom, which is 7.3. And we get an F statistic of 3.794 and statistical significance at the 0.05 level. So yeah, so that's I just wanted to demonstrate how we end up calculating the different sum of squares. All right, so got to stop. Take care. Bye.